We know that the absolute time of Newton has been displaced by the relativity of time. Physical processes take place more slowly when the system being observed is in relative motion. Moving clocks beat more slowly. Let's see where this leads us. We'll start with the light clock, which works by bouncing light pulses between reflecting walls. When the clock is stationary, a pulse of light moves back and forth in a certain time. But when the clock is set in motion with speed v, the light traverses a longer path and takes a longer time for one tick, one period of the clock. The increase in time is given by the factor gamma. Now we're going to use these same reflecting walls to draw some other interesting consequences of special relativity. This time we take two vertical walls and we imagine a light source sending out pulses from the center toward the walls. Since they have equal distances to travel, the pulses reach the walls at the same time and return to the center also at the same time. Now let's imagine a similar setup as a kind of signaling system inside a spaceship so that the light reaching the walls this time is picked up. A large space station is nearby observing everything. Relative to the observing station, the signaling spaceship is in uniform motion. How will the light pulses be observed to travel? Now the left wall advances to meet the light pulse, while the right wall retreats. So to the observer in constant motion relative to the spacecraft, the consequence of light traveling at its invariable speed is that the two light pulses hit their respective walls at different times, the left-hand event here occurring earlier. If the spaceship were moving in the opposite direction, it would, of course, be the right-hand pulse that would arrive first. But notice, as before, that the light pulses always travel at constant speed c. Depending upon the relative motion of the observer, then, these events occur at the same time or at different times, in either order. All right, but now let's change the signaling system. Let mirrors be installed at the ends of the ship so that the light pulses are reflected back to the center of the spacecraft. How will this new signaling system operate when observed from the passing space station? So the time situation will be reversed on the return trip, and the two light pulses return to the center at the same time, simultaneously. Simultaneous events at the same point in space are simultaneous for all observers in uniform relative motion. But two events at different spatial points that are simultaneous for one observer are not simultaneous for another observer in constant relative motion. Does that mean that a simple act like this could appear to another observer as the ball landing in my hand before I drop it? No. The reason is that there is a physical object in motion throughout this act, and any observer at whatever relative speed will be able to follow it and has no choice but to agree on the same sequence of cause and effect. This situation did not apply in the case of the spaceship, as the two light pulses had no cause and effect relation. The absoluteness of the speed of light, in the sense that no material object can ever attain it, was fundamental to the conclusions we have just drawn. But one thing we have not asked is this: what mechanical property prevents that limit from being attained? What is it in the nature of matter that makes the speed of light inaccessible? One way to investigate this question is with atomic particles, and in doing so, we shall be led on to further implications of special relativity.
When protons are channeled down long vacuum chambers, very fine beams can be produced, and these can be manipulated with very great accuracy. Inside particle accelerators, like this one at the European Nuclear Research Organization near Geneva, bunches of protons are driven up to very great speeds by electric fields. These are cleverly timed to keep urging the protons ever faster. This proton synchrotron, as it's called, was built in the shape of a ring, about 200 meters across. It produces protons traveling within a fraction of a percent of the velocity of light. In 1976, the protons from this ring were injected for the first time into a giant new ring of magnets many times larger than the proton synchrotron. Buried beneath the soil, this super proton synchrotron measures more than 2 kilometers across and is one of the most powerful machines ever made. Once inside the SPS, the protons are again subjected to strong electric fields. These urge the protons on, so that eventually they end up with 40 times more energy than when they entered. But remember, the protons started in the SPS at almost the speed of light. So what happens to their speed as the energy goes up? Well, there's the energy going up. It goes up from 10 GeV up to 400, which was the factor of 40. But look at the velocity. It goes up in the first phase of the acceleration quite quickly to almost the speed of light, but then it just flattens off. How can we explain that? How can you push something along so that it gets more and more energy, but it doesn't go any faster? Well, it must mean that the inertia of that particle is going up. Its inertial mass. And we can show that, too, on this output. There in the center of the screen, you've now got the mass displayed. As you see, it's going up along with the energy. And that has to be the explanation of why it is that you can't push a proton or any other particle faster than the speed of light.
We are now going to give a precise form to the idea that mass, or inertia, increases with the speed of the body. We shall apply the concepts of special relativity and the conservation of momentum. Let me start by reminding you of that conservation law with the aid of this simple toy. Clearly, all the momentum of one body is transferred to the other on impact. We can repeat it using effectively twice the mass. And the same thing happens. But now, let's use bodies of different masses. We can see that the heavier mass acquires a smaller speed. This becomes more interesting if we set both balls in motion. The momenta of both balls are being reversed on collision, and the heavier ball is clearly moving more slowly, just as demanded by the conservation of momentum. We are now going to combine these two ingredients of momentum conservation and the concepts of special relativity in a kind of space game. A spaceship at rest is designed to fire a projectile broadside. Now, two spaceships at rest do the same thing, firing towards each other identical projectiles that move at equal speed. They collide and recoil along the line of fire. Let's concentrate just on the velocity of the projectiles before and after the collision. It's clear that the projectiles carry equal and opposite momenta. The total momentum is 0 before the collision. And it is also 0 after the collision. Momentum is conserved. No problem here, but that's not a very exciting game, so let's add another ingredient. Suppose we now move rapidly relative to one of the ships, or equivalently, one of the spaceships is moving rapidly relative to us. How do we perceive things? As you remember, lengths along the line of motion are contracted. All right, but how about the act of firing? You will also remember that time significantly slows down, so the act of firing the projectile from its mothership is slowed. As the spacecraft itself is moving, let's look at it again in a way to emphasize the transverse motion of the projectile. Well, so far there's nothing new. We have seen the conservation of momentum and the effects of special relativity. Now we combine them in a new game. Let the two spaceships move relatively to each other. Each of them fires its projectile. Let's look at that end on to concentrate on the transverse motion. Clearly, momentum conservation still holds. How does the same collision look when we move with that spaceship A? That is, when A is at rest relative to us. Obviously, A fires broadside. B, being in rapid motion, exhibits all the time-slowing effects we have discussed. How does the whole incident look? There's something different there. B fires first. By changing frames, we've lost the simultaneity of firing. That's just what you would expect from our discussion before. But we want to concentrate on something different here. Let's look at it again from the N view. The transverse velocities of the two projectiles are different. Yet this is just another view of the collision where the two velocities were equal, where there is no doubt of momentum conservation. All that has changed is the frame of observation. So momentum should still be conserved. How do we reconcile this? The heavier ball is moving more slowly. There's the answer. Very good. Here, as anticipated, is a mass that grows and grows as the speed approaches the speed of light. And the effect of that is to prevent the speed of light ever being attained by a material body. But that's not the end of the story. The gamma curve used V over C as the horizontal axis. It doesn't look very different if we change that axis to the square of V over C. But suppose we magnify the beginning of the curve for very small values of V over C, where gamma is slowly rising above unity. We get a straight line, and its slope is a half, or in symbols, gamma minus 1 equals a half V over C squared. So the mass at low speeds is given approximately by this. The combination of a half mv squared is the Newtonian expression for the kinetic energy, the energy of motion. And we see that an increase in energy of a half mv squared produces an increase in mass equal to 1 over c squared times that increase in energy. Or delta E is delta m c squared. Here is the relation usually presented as E equals mc squared that has become the hallmark of Einstein's theory of relativity. That mass in its totality can be converted to energy is a very strong statement indeed. It goes beyond the partial conversion of mass that fuels the sun and nuclear reactors. Well, in what kind of environment can we find direct evidence for it?
To look into this interchangeability of energy and mass, we come once again to CERN with its world of high speeds and big accelerators. Now, you remember I said that the superproton synchrotron accelerated the protons to very high energies. What happens to that energy? Well, the particles are fed off from the SPS into a number of different detectors set up to study the way the protons behave. Inside this huge magnet is a detector called a bubble chamber. It's a device for taking pictures of subatomic tracks. This one contains some spectacular secrets of what can happen to a proton. In a bubble chamber, what happens is this. Particles from the accelerator are passed into the tank of liquid hydrogen. As each goes through, it slightly warms up the liquid along its path. A little while later, tiny bubbles of hydrogen gas form. These bubbles grow to be much larger than the particles that cause them. And once they have grown to a visible size, they can be photographed. And this gives us a permanent record of the particle's paths. When you realize that you're looking there at a record of a particle that is only a millionth the size of a pinhead, you'll appreciate the incredible ingenuity of the bubble chamber. Now, the paths of the particles, or as we call them, bubble chamber tracks, they're examined on a scan table like this one. It's here that the secrets of the particles are revealed. And the way it's done is that we examine these tracks and we measure them up, and the data is fed off into a computer. And from the characteristics of the track, that one is able to infer just exactly what that particle was doing as it was going through the liquid. Well, what does it do, apart from make a track? Well, most of the time, it does nothing. The atoms of the liquid are mostly empty space, a tiny nucleus, which in hydrogen is a proton, surrounded by an even tinier electron. So the particle just coasts along and passes out the other end. Sometimes, however, the particle scores a direct hit on one of the protons. And then what usually happens is that the particle bounces away and sends the struck proton off in the opposite direction. This recoiling proton has enough energy of its own to create a track, and so we end up with two tracks instead of the original one. And this is just such a photograph. You see the track of the incoming particle on the right and the two outgoing ones on the left. Well, that's just a simple collision, not very interesting, just to help us get used to the idea of looking at these bubble chamber tracks. But there's something very much more interesting on the next photograph, so let's bring it up. But this time we've got four tracks. Well, two of the tracks obviously correspond to the incoming particle and the recoiling proton. But what are the two extra ones? Well, they have to be caused by particles of some kind, and they would be particles that were not present before the collision. So where do they come from? Well, when measurements are carried out on these tracks, it turns out that the energy carried by the four final particles is less than the energy of the incoming particle. We can arrive at this conclusion by the characteristics of their tracks. Remember I said that there was a magnetic field on the bubble chamber. Well, the purpose of that is to curve the tracks, and the amount of curvature depends upon the electric charge carried by the particle and its momentum. And from its momentum, we can get its energy. Well, as I say, when you do this calculation, it turns out that you end up with less energy of motion after the collision than you had to begin with, that was brought in by the original particle. So, energy missing and two new particles created. Well, you've guessed it. What's happened is that some of that original energy of motion brought in by the particle in the accelerator has been transformed into the matter of the two new particles. It's an example of the interchangeability of energy and matter. We have an even more convincing demonstration of that on the next photograph. Well, straight away you'll see that it's a much more complicated picture than the previous one, so we'll have to take this in steps. Once again, the particle comes in from the right. As it collides with one of the protons in the liquid, it produces 6 tracks. In other words, 4 new particles. But having said that, you'll notice that we haven't yet accounted for all the tracks on the picture. And the reason is that as well as the production of 4 new particles, a pulse of light is also created. You can't see it on the photograph because light does not leave a track in the bubble chamber. But in point of fact, the light crosses over to there and transforms itself into 2 new particles. One is an electron, and the other is a positively charged electron called a positron. Now, this is an example of the transformation of pure energy, pure electromagnetic energy of the light pulse into matter. Right now, what happens to these 2 new electrons? Well, the negatively charged one goes spiraling off into the distance, gradually losing energy to the liquid until eventually the electron stops. But meanwhile, what's happening to the positron? Well, it starts off in its characteristic spiral, but then it hits one of the atomic electrons belonging to the liquid and transforms back into light. So that's the kind of thing that happens here. With the bubble chamber technique and with other techniques, we can investigate this interchangeability of matter and energy. And all these interchanges are taking place according to Einstein's equation E equals mc squared. Right, well, there's one final point that I want to make, and that concerns the exchange rate. How much energy is required to produce a certain amount of matter, and vice versa? Well, I can illustrate that in the following way. Suppose that coin were made from positrons, and this one is from ordinary electrons. Suppose we brought the positrons and the electrons together so that they could annihilate in the way that we've been seeing in the bubble chamber picture. How much energy would we get out of that? Well, the answer is the equivalent of 40,000 barrels of oil, which is pretty staggering. And that, in fact, explains the enormous power that we get from nuclear power stations and from nuclear bombs. Those are processes which give rise to very efficient changing of matter into energy. It also explains why CERN requires those enormous accelerators to produce even these tiny bits of matter on these photographs.